proximity of magnifications. Okay, so in the last example, what we saw was that it's impossible to get square root of 2 accurately. Instead, we have to work with its approximation, which is to 1 decimal place, which is correct to 1 decimal place. And so we therefore know that if it's correct to 1 decimal place, then the distance between 1.4 and square root of 2 is at most 0.05. Okay. Then we saw that we did the same for square root of 3, correct to 1. 1.7 is correct to 1 decimal place. So in the same manner, it was within 0.05. Then we saw that instead of square root of 2 plus square root of 3, instead of using that, instead of using that, we use the approximants, 1.4, which is exactly easy to calculate, 3.1. Then we saw that so this, remember, these are called deviation bounds because it deviates from square root of 2, square root of 3. Okay, so we saw that the deviation bounds actually added. So remember that this is we wanted to see what is the knock-on effect of if 1.4 and 1.7 are off from the actual square root of 2 and square root of 3, then how much off is their sum, 3.1, from the actual root 2 plus root 3. And this knock-on effect, error is called the error bound, because it is induced by we give it a different name because it was induced by the previous deviation bounds delta 1 and delta 2. And then we saw that it was actually the sum of the two. Okay, so the knock-on effect is the sum of the errors in both of the terms, in both of the summands, 1.4 and 1.7. Okay, now we look at the process, instead of addition, we now look at the process of magnification. So we now know that 1.4 it deviates from square root of 2 only by 0.05. The big question we now ask is that what about 5 times 1.4? Yeah. So now we're going to look at magnification. So let's say I magnify square root of 2 by 5 and the approximate of square root of 2, which is 1.4 by 5. How much does this differ by? Okay. And one can take an educated guess that, so if we follow the pattern, so previously if you added, then the deviation bounds added. Here, if we magnify, then one can reasonably think that the intuition is that the error bound should be, let's just call this delta, should be equal to 5 delta, which is 5 times 0.05, which should give me 0.25. Okay, this is just our intuition. So let's actually test it out. Okay, so remember that the whole idea. Okay, so we want to see how much does 5 times 1.4, the approximate, differ from the actual 5 times square root of 2. So in this particular case, what I do here is that the key to doing this is to try to reduce it to the previous distance or deviations that we know, which is the deviation from 1.4 and square root of 2. So we have to find we have to relate these two. So what we do here is that we make use of this rule of the absolute value, that if I take the absolute value of a product, it's the same as the absolute is the product of the absolute values. Okay, so what I do here is that when I look at this 5 times 1.4 minus 5 times square root of 2, the only reason why I will factorize out the 5, why I will factorize out this 5, is simply because I want to expose expose the known 1.4 minus square root of 2 term. So what happens here is that, so when I factorize it out, so it's going to be 5. Then I factor out the common factor, and then I end up with 1.4 minus square root of 2. Okay? So notice that, so now I've got the absolute value of two terms, 5 and 1.4 minus square root of 2. And so by the law of absolute values, that is going to be equal to the absolute value of 5 and then times the absolute value of 1.4 minus 1.√2. Okay? So what is happening here is that an absolute value of 5 is nothing but 5 times the distance between 1.4 minus square root of 2. But we know that this is at most 0.05, so, or delta. So it's 0.05, which is our delta. And so we therefore prove our intuition correct, and we get 0.25. Okay? So notice that in the general case, what happens here is that, so let's bring some letters in this case. Okay, so now the next question is, in the general case, where we have, so the general case is that given, so I know that this x, it deviates from square root of 2 at most by delta. So this x is playing the role of my 1.4, okay? Then the question is, so in the general case, given that, x is within delta of square root of 2, then what about 5x compared to 5 times square root of 2, okay? Then what is the corresponding error bound that results from this? Okay, and as the intuition would say, that the corresponding error bound should be 5 times delta, as we saw, 5 times the original deviation bound. Okay, so what we then do here is that let's actually prove it using that same trick that we were using. And so remember, so we take this unknown deviation, unknown distance, and we try to express it in terms of our known distance between x and square root of 2. So in this case, if I get 5x minus 5 square root of 2, then I can factorize out the 5, so I can expose the x minus square root of 2 term, and the absolute value of, remember this is a product, is going to be the product of the absolute value, and so therefore I've now exposed this. Okay, and so this is nothing but 5. The absolute value of 5 is just 5 times x minus square root of 2. But notice that the most that x minus square root of 2 can ever get is delta. So this will give me 5 delta. Okay, so here we actually have got 5 delta, right? So the error bound epsilon that results from the original deviation bound delta is just 5 times it. So you just magnify the original error of delta. Okay. So so that brings us to the end of the of this magnification section, and the next section that I want to then move on to is going to be with circular functions. Okay, and here, so we're going to now do some proximity that is going to involve circular functions. Okay, but before we move on, let me just give you what happens in practice now. So what happens in practice is that, so remember that in the general case, it was given that that x, which plays the role of the 1.4, deviates at most from the square root of 2 by delta, then how much does 5x deviate from square root of 2? Okay. Okay, so this was a natural way to look at it. But what actually happens in practice is that this epsilon, so normally what happens, okay, so to make these things easy to understand, we started off, this was known to us, that delta was known. So we knew, for example, that like if x was 1.4, that it was correct to 1 decimal place. So therefore, we knew that my delta was 0.05. And so therefore, the corresponding error bound that comes from working with this wrong or with this inaccurate x is going to be 5 times the original error, which is delta, which is 0.25. Okay. Now, but what happens in practice is that we normally work backwards, in the sense that what we do is we say that if I know epsilon, so we normally think of the epsilon as the known, let's say it's some known challenge. Okay, so if I know my epsilon, then the question is find a delta to rise to the challenge of the epsilon. Okay, so let me say that slowly. Let's look at this very carefully again. Okay, so what happens is that I know that if my x is within delta of square root of 2, then I am guaranteed. So if I know this is true, then I'm guaranteed that my 5x will only deviate from 5 square root of 2 by at most 5 delta, which is our error bound epsilon. Okay. Now, so in this case, my epsilon is equal to 5 delta. But what normally happens in practice is that the epsilon is actually given to you. This is what happens in practice. So basically, I say to you is that I want my 5x to be, so let's say that, okay, let's be concrete. Let's say my epsilon is equal to 1. Then I will say that I want my 5x and my 5 square root of 2 to be within, I want my 5x to be within distance 1 of 5 square root of 2. Okay, so this is what's going on here. So here this is 5 square root of 2, and I want, so it must be within distance 1. Okay, so this is 5 square root of 2 plus 1, 5 square root of 2 minus 1. Okay, and so this is my 5x. Okay, let's just draw him in red so that he looks a bit different. Okay, so this is, okay, blue. Okay, my pen colors are kicking in. Okay, but you know what I'm saying. Okay, so so what we have here is that I've got what is called 5x. Okay, so I want my 5x to lie within distance 1 of 5 square root of 2. Okay, so the big question here is that in order for this to be guaranteed, how close must my x be to square root of 2? So this is my x, you see. So in other words, for 5x minus 5 square root of 2 to be within distance 1 of 5 square root of 2, the question is what distance must I get x to be close to square root of 2 in order to guarantee that my 5x will be within distance 1 of square root of 2. Okay, so this is square root of 2 plus delta and square root of 2 minus delta. So that's the big question. So we see we're asking the question backwards. Now I know that, remember that when you magnify something, the original error from square root of 2, which is your delta, this guy, he gets magnified by 5. We've seen it over and over, about 3 times, okay? So obviously, because my epsilon, which is 1, is equal to 5 delta, this would therefore force me to say, okay, so if my delta is 1 over 5, then so if I can get my x to be within 0.2, which is 1/5, or 0.2 within, so this is square root of 2 minus 0.2, square root of 2 plus 0.2. So if I can actually get my x within 0.2 of square root of 2, then my 5x will definitely be within 5 times 0.2, which is 1 of 5 square root of 2. Okay, and so this is often how things actually turn out in practice. Is instead of going from deltas to epsilons, as we have been seeing, we normally go backwards from epsilon to deltas, and we say that so we can do this for the general case. So in this case, so let's solve this for the general case, okay? So for what delta does x minus square root of 2 guarantee that 5x minus 5 square root of 2 is smaller than epsilon? Okay, so in that example, we saw that our epsilon was actually equal to 1. Okay, so in this case, so remember that we now know that remember that we know that epsilon is equal to 5 delta. Okay, so in this case, we think of our epsilon like 1 or whatever, but we think of it as the challenge. Okay, so what we say here is that, okay, so what we are saying here is that, okay, so we want, so in this particular case, so in this case, if so think of epsilon as 1, then the delta that will rise to the challenge will just be epsilon over 5. So remember, in our previous example, our epsilon was 1. So what is happening graphically is the following. Okay, so here's my mapping diagram. Okay, so what I have here is I've got square root of 2, and I've got some x which is within delta of square root of 2. So this is square root of 2 plus delta, square root of 2 minus delta. Okay, so my x is somewhere in between here. So x is somewhere in between here. Now, so what happens here is that, now remember, I magnify everything. So I've got 5 square root of 2, but I am playing difficult by saying that, look, I want you to find, I want the 5x's. Okay, so this is my 5x's. So I want my 5x's to be within a certain epsilon. So it's, I set the challenge. So it's 5 square root of 2 plus epsilon, 5 square root of 2 minus epsilon. So I actually want my 5x to be within a given, so think of the epsilon as a challenge. So my epsilon is like some known number. In our previous example, it was 1, but it could even be a difficult or a hard epsilon. So it can be like a tiny one, making it very, very difficult, like 0.0001. So I want, in order for my 5x to lie within 0.0001 of 5 square root of 2, give me a delta where my x must lie within square root of 2 in order to actually get it to be within 0.001 for my 5x to lie within 0.001 of my 5 square root of 2. So in this case, remember, because the arrows always magnify when you do a magnification operation, so in this case my delta will always be epsilon over 5, which in this case is 0.001 divided by 5. And then in this particular case, if I can get my x's within 0.001 0.0001 of 5, then it simply means that I'm guaranteed that my 5x's will be within 0.001 of 5. And then in general, if I can make my delta, within epsilon over 5 of square root of 2, so it's epsilon over 5 of square root of 2, this will definitely then, because remember that everything just magnifies by 5, it will mean that my 5x over 5 square root of 2 will be within epsilon of 5 square root of 2. So therefore we think of epsilon as some known number divided by 5. So this is what happens in practice, is that the epsilon is thought of as the known number, and then we try find the corresponding delta to rise to that challenge. Okay.